So just a reminder, we talked about empirical formulas last class. So it was the smallest whole number ratio of an atom, of a molecule, of the smallest ratio of atoms in a compound. So we were looking at, for example, CH2, or C2H4, C3H6. Going through any of those, the smallest ratio is 1 carbon to 2 hydrogen. So our empirical formula, no matter which of these is actually true technically, the empirical formula is CH2. And then we talked about how that actual mass was determined, or how those empirical formulas are determined. So we're finding the mass of things and then working backwards from knowing the mass of the different elements in the compounds, to find that formula. So what we did, were a couple examples where we had a compound that had 43.2 grams of carbon and 115.8 grams of oxygen. And we found the mole ratio between the two. And then we used that to figure out that there was 1 carbon for every 2 oxygen by dividing both of the number of moles by the lowest number. And we figured out that this one was CO2. These ones are really nice and straightforward. When we end up with like a 2.01 to 1 ratio or something, we can just go, okay, it's 1 to 2. But then remember, when we were kind of closer to the end of the day, we were talking about, okay, what if I go through this process and the smallest ratio of moles ends up being like 1 to 1.5? In that case, 1.5 isn't close enough to 1 or to 2 that we can just say this is 1 or 2. So what we do is we multiply it by a number. We multiply both of them by a number that makes this a whole number. And we ended up, in this case, with a 2 to 3 ratio. And our empirical formula was Fe2O3. So this is just kind of reviewing last class, you guys. And then in our last example that we did, we ended up with a bit of a tricky number, where we had 2.67 as one of our numbers. So did everybody have a look at that chart that's on page 93 of your textbook? Yeah? Did anybody not have a chance to look at that? Okay. So you do need to know that. There's a chart on page 96 of your textbook, page 93 rather, and it's got just some common fractions that you guys need to be able to recognize their decimal equivalents. So these fractions are really going to be important, because when you find something that's like 0.67, 2/3, which is what we found here, you need to know what you can multiply these by to clear the fraction. So commit these to memory, make flashcards, test yourself on them, whatever you need to do there. Okay. And then we had these practice questions, page 93, number 46. Did everybody get a chance to work on those? Were there any of these that people had a hard time with and want to go through together? You're feeling okay about this? Pardon? What page? We're just on page 3 of the note set. So we're page 3 of the 5.5 note set. And we're just going to continue with it unless somebody wants me to go over any of these questions. Okay. All right, I'm going to move on to talking about molecular formulas then. Okay, so empirical formulas and molecular formulas are a little bit different. The molecular formula is some whole number multiple of the empirical formula? Okay, so we know, for example, H2O2 is the hydrogen peroxide molecular formula. But that is actually not the lowest whole number ratio, right? So if we were to find the empirical formula for that, what would it be? Lowest whole number ratio for H2O2. What do you guys think? Yep, HO. But that's not what hydrogen peroxide is. So the empirical formula would be HO. So therefore H2O2 is the molecular formula. So in order to find that multiple, in order to figure out what we actually have, we have to use the molar mass of the compound and what the empirical mass would be. So you're a chemist back in, well, I mean, I guess this could be a chemist currently. You're a chemist and you are, you're figuring out what a compound that you found is. And you work out that, okay, this compound has, let's say, which is one of the examples we did, you work out, okay, this compound has got 42.3 grams of carbon and 115.8 grams of oxygen. So you go through this process and you determine the the empirical formula. But what you know is that that empirical formula that you determined is in the lowest possible terms, and that might not be what the actual compound looks like. So then what you're going to do is you find out using kind of like a little bit higher level technology, but you can find out the actual molar mass of the compound, and then from the empirical formula, you can figure out what the actual ratio is in that compound. So what you do is you go molar mass of compound. So the molar mass of the compound is just determined using kind of advanced like chemical technology divided by the empirical mass. So what we've found by figuring out the percentage or the ratio of compounds. And then that is going to give you a multiple, which we call N. And that multiple is going to be what you multiply your formula by in order to get the proper number. So for example, you might determine that the N value for HO would be 2. And then you would get H2O2. So what I could do is I could actually take a liquid. I could put that liquid into a separating device that has an electrical charge running through it. And I could measure the amount of hydrogen I got and the amount of oxygen I got. I could determine what the empirical formula was based on that information. But then I would have to find the molar mass of that compound, divide it by my empirical mass that I found, and then, oh, it's 2. What I've got is hydrogen peroxide. Does that part make sense? The theory behind this? Yeah? Okay, good. All right, so we are going to do an example here. So a compound has an empirical formula of CH2O, but its molar mass is 180 grams per mole. So what we need to do is figure out its molecular formula. So the molecular formula will be CH2O bracket N. So that N is my multiple, where N is some whole number. And that whole number is going to be given to us by the formula that we have up here. Okay, so the empirical mass of CH2O, I've got carbon is 12 grams per mole, right? I've got 2 hydrogens, so 2 times 1. And then I've got oxygen, which is 16. And I've got 30 grams per mole. So if the empirical formula that I determined was correct, the molar mass of that compound would be 30 grams per mole. But is that the molar mass? No. So what we need to do is go N equals my actual molar mass, which is 180, divided by my empirical molar mass, which is 30. And what I'm going to get is 6. So therefore, the molecular formula is, so I'm just going to go through the process of getting from there. So CH2O, my N value is 6. So I'm going to multiply each of these subscripts by 6. And I'm going to get C6H12O6. And I'll bring this up a little. Okay. Did I lose anybody in that section, or are we feeling okay? All right. So what if you are not given that molar mass? So you can also figure this out if you're not given the molar mass of the compound, but you're given other information instead. You need to interpret that information that's given and use the skills that we've already developed, like what we just did with the chalk, to find the molar mass. So you might not be given molar mass. You might need to get there from other information. And then you are going to have all the info you need. Okay, so in this example, I'm given SiH3, and I've got 0.0275 moles of that compound has a mass of 1.71 grams. So I'm being asked for the compound's molecular formula. Now I'm not given the molar mass, but I do know how many moles has this mass, right? So what you can do from there is figure out the empirical mass first. That's always our first step when we're doing this. Empirical mass. So I've got silicone, which has got a molar mass of 28.1 grams per mole. And I've got 3 hydrogens, which has got a mass of 1. So I end up with 31.1. Whoops, not 3, 30.1. That's a 1. Grams per mole. All right. Now, what's our molar mass? How would you guys determine molar mass if you're given that you've got 0.0275 moles and you've got 1.71 grams? Exactly, yes. Okay. So grams per mole, 1.71. Man, I'm messing up my numbers today. 1.71 grams every 0.0275 moles. So we would just divide those numbers and we would end up with, all right, I have got a molar mass of 62.2 grams for every mole. And then from that information, can I find my N value? Okay, which of these numbers is being divided by which? Yeah, so I'm dividing my molar mass by my empirical mass. So the one that you found, the molar mass, is going to go on top. So I've got 62.2 grams per mole divided by 31.1 grams per mole. And I've got an N value of 6. So molecular formula SiH3. Oh, whoops. Why did I write 6 there? Sorry, it's 2. Oops. Okay. SiH3, and I've got an N value of 2. What is my molecular formula? Good. Si2H6. Nice work. All right. Let's do one more. All right. So a gas has got an empirical formula of POF3. And I know that 0.350 liters of the gas at standard temperature and pressure has a mass of 1.62 grams. I want to know the molecular mass of this, or sorry, I want to know the molecular formula of this compound. So first up, I want you all to find the empirical mass, okay? So take a second to do that. Empirical mass of POF3. Does everybody have an empirical mass? You do? What is it? Oh, okay. Empirical mass. Oh, I think I heard it. Yeah, 104. Nice. Okay. So then what we need to do is we need to figure out the molar mass. How are we going to get the moles? What do we have? We've got volume. So we're going to have to go from volume to moles. Okay, so let's do that. I've got 0.350 liters. And then I know that at not room temperature, at standard temperature and pressure, there are 22.4 liters of gas for every 1 mole. What's going to go on the bottom, liters or moles? Good. Okay, and then we should end up with how many moles? 3.350 divided by 22.4? Yeah, divide. Yep. Okay, so that's how many moles I have. When you're answering a question, you do want to make sure that you're using the correct number of sig figs. When you're actually going through calculations, the more numbers you keep, the better. Yep. 22.4. So at standard temperature and pressure, 1 mole, yeah, 22.4 liters. Good question. All right, and then I need to figure out my molar mass. So molar mass is grams per mole, and I know that I've got 1.62 grams, and I've got 0.015625 moles. Do you all know how to save your answers and then use them later in your calculator? .62, yeah, sorry. My zeros and my sixes sometimes look very similar. Okay, it's a little bit different on each calculator, but I would recommend just finding out how to save your answers and then bring them back later. It's usually like second function answer or something. It can be really useful when you're trying to keep as many digits as you can. Okay, so my molar mass is going to be that divided by this, which hopefully gives me 104 grams per mole. Do you calculate it the same way? Like, how do you mean? Yes, so normally if you were given a molar mass, you would calculate it by adding together all of the things in here. But we're just given, this is the empirical formula. And we don't actually know what the molecular formula is. So we can't calculate molar mass by adding the masses together because we don't know what it is yet. So that's why we're going through this process. So we're kind of like working backwards. So we're kind of going the opposite way that we normally would to get to molar mass. Oh, I forgot to send down the lunch order. Okay, we'll just finish this up and then we'll order lunch. Okay, so if I then find my N value, it's 104 divided by 104, so it's 1. So in this case, my molecular formula is actually the same as my, so technically I go like this, 1, and then POF3. So my molecular formula in this case is the same as my empirical formula. Okay, does everybody understand why we're finding molar mass this way? Okay, I want you all to give these questions a go. So page 95, 47, 51, 54, 55. If you are having a hard time with one of those questions, let's go through it together as a class. And then I've got a worksheet up here as well. We need to do lunch orders. So if people would be able to just put in their orders for lunch, if you want